Hello everyone, my name is Ben Mullen. Today I'll be presenting What is the Future of Fusion Energy by Philip Ball. I'll be doing an executive summary. And I'd like to start off by explaining exactly what nuclear fusion is. Basically, it's two nuclei combining to create one large nucleus. And we do this typically in the form of plasma. And when we're doing this, it outputs immense amounts of energy. But in order for two neurons to collide, you need to create very, very special conditions, and I'll be going over what that kind of looks like. So basically, the sun is one ginormous continuous fusion reaction, and so in order for us to recreate a fusion reaction, we have to mimic the conditions of what the sun is in, which is immense amounts of density and very, very high temperature. We're talking like 100 million Kelvin, and you might be wondering, how do you contain 100 million Kelvin? Because obviously we can't just like hold it or put it in a jar. We put it in the state of plasma, and we confine the plasma. In a tokamak design, it's like almost a donut. We confine the plasma with magnetic field, magnetic confinement. And another obstacle that comes up is tritium. So this reaction takes deuterium and tritium. Deuterium is very prevalent in the ocean. It's very easy to come by. Tritium is a little more tricky. It's not commonly naturally produced. Produced very small amounts naturally, and it has a half-life of about 12 years, so it's constantly coming and going. But there's kind of a little workaround. You can put lithium on your fusion reactions to the reaction with lithium, and the fusion reaction generates a little bit of tritium. There's kind of a little workaround, but another thing is insufficient surrounding material, because these colliding neurons, occasionally they will collide with the outer wall. Now, either we need some type of structure or material that can withstand that collision, or we need some type of different design to avoid that from happening. So obviously the tokamak design is the most common design, which is, like I said, the donut with the magnetic confinement. Philip Ball touches on the International Experimental Thermonuclear Reactor, which is a mega project, like $20 billion budget. Plasma is 6.2 meters in radius. It's a mega project that's been going on for a few years now, and is not expected to be done like until another 2 decades. It's basically just a massive scale tokamak design. Another design is a spherical version of the tokamak design. This was a great step because it makes a compact version of the tokamak, and that's crucial because compact means cheaper to produce, and that means it introduces smaller companies into the fusion competition. Having these smaller companies in this race of commercialization of fusion energy is crucial, because what they do, they can participate in finding out specific areas of the problem. So like Spark was a design created by a smaller company. So basically MIT created this specific magnetic confinement, which is way, way more effective than anything anyone else has ever done for the fusion magnetic confinement. So the smaller company, they didn't have billions of dollars. They just produced this magnetic confinement phenomenon, and then all of a sudden they've contributed largely to the commercialization of fusion energy. So these smaller companies participating is crucial to the future of fusion energy. So all of them, they'll either be providing expertise, or they'll be supply chain for the bigger companies that eventually are the ones commercializing it. So they're crucial. Philip Ball also touched on the stellarator and the NIF design. NIF is National Ignition Facility, but the stellarator is potentially the most effective at confining plasma. This was stated by the father of the tokamak design, and you can see by the picture right here, it's very hard to engineer and practically provide commercialization with this design because it's very hard to engineer. It's an engineering crisis. The NIF design is the National Ignition Facility. They were basically testing out nuclear power. They weren't trying to produce some fusion technique. They basically came across this on accident. It's basically the process of not this tokamak design. It's like the ignitions of deuterium and tritium mixture. Basically, it's several ignitions in the span of a second to get pulses of energy, and you need to do this constantly, or else this pulse will go away. So you need tens of ignitions per second to get this pulse of energy to like ignite the reaction. The future is hard to predict for the fusion timeline, because like it's been a conversation for so long, and there hasn't been massive strides. Specialists are saying around 2050. It's just hard to tell because these reactors, they take a decade to produce. They're not something I can just up and go right away. We don't have the knowledge we need right there. We're still in the testing phase of everything. But it will be the future of energy production just because of how much output it has and how cleanly it is. And that is a big topic that's been going on for the last couple of years, especially, is clean energy. But yeah, this is Fusion Energy, and my name is Ben. Thank you for listening.